Actually, before I get to housekeeping stuff, any news? Nothing interesting happened in the world in the last week.
Possible.
Yeah.
There was a study that came out of MIT that showed that it's more expensive to get a fake digital signature than to make a fake passport or a fake.
What is a fake digital
Not
signature?
a fake digital signature, but to acquire a digital signature from trusted software. Steal a digital signature.
Okay, got it. Or something like malware.
Yeah, exactly.
Okay, that makes sense. So it's more expensive to get a digital signature.
Then to copy a to get a fake passport or a fake contract.
Those things seem like they're not quite comparable, right? Like we're talking about a piece of software you can install on hundreds of thousands of people's computer versus one fake passport or something like that. But that's interesting. So I wonder how the methodology of that looked like. I'm not quite sure.
It was on like a huge, they basically did like a really big dark web like sweep and came up with all the information they had on how much everything costs.
Okay.
And
Okay, interesting. Okay, so there is this kind of measurement work where people go out and they look at these kind of criminal markets, particularly the dark web, and they say, how much does it cost for me to do bad thing X? And it's really interesting when they find out that bad thing X is like something interesting, like get a forged digital signature. How do you steal a digital signature for a piece of software? I mean, how is that done in practice? Like, how do you go about stealing a signature on your software? How do you even do that? Like, what does that look like? What is the actual attack?
Don't you need to attack the certificate authority?
Okay, so you can attack a certificate authority, that's fine. So remember, what do these things look like? Typically, you have a certificate authority up top, listed VeriSign every time. Pick a new one, let's say it's Thought. Okay, so Thought is a certificate authority, but usually Thought doesn't sign every piece of software because that sucks. So what they'll do is they'll say, you know, like there'll be some company, let's say it's, you know, US Robotics. Does US Robotics even exist? I don't know anymore. But let's say US Robotics then will get their own public key signed by Thought and get a certificate, right? So they'll get, you know, a cert that basically says we're US Robotics. And now when they want to manufacture a driver that they want to ship to Windows, they will use the secret key to then produce a signature on a driver. Okay, so there's two levels to this. Sometimes there's more stuff that happens. Sometimes there's like another CA up here that's actually making a certificate chain. This is one of the things about certificates. They can be chained relatively high. You can have 20 levels of certificates. But let's say you just have this kind of level of thing going on. So there are a bunch of attacks that you can do. You can attack Thought. You can try to trick them into giving you a signing certificate. Maybe Thought will stop you from doing that because I think you have to like write them a big check to do that. So that shouldn't be very easy. But obviously, you could then find the person who's holding on to the secret key for US Robotics. You could send them a phishing email and get them to send you the key, or you could hack into their systems. So a lot of these kind of software signing certificates come from the fact that somebody has hacked into a manufacturer. Does anyone know where the Stuxnet? Anyone know what Stuxnet is? Yes.
Stuxnet is a product of the collaboration between the NSA and the Israeli government that brought down the Iran nuclear
centrifuges.
Good, and parts of that malware were signed. Anyone know where the signing key came from? Anyone, you know? I think it was I'm guessing, I think it was a Taiwanese manufacturer, some manufacturer, I don't know what equipment they made, but they had been given a signing certificate, and somebody got their secret key, and, you know, presumably by hacking into them, and they used that to sign the Stuxnet malware. Why does that matter? Why do you want to sign your malware? Why is that so good? Why can't I catch a piece of chocolate? Why do you want to sign your malware?
Because the antivirus will not catch it.
Good. So most antivirus will ignore or whitelist certain pieces of signed software because they'll say, hey, they have a legitimate signature on it. That's a really good indication it's legit, especially if it's like a Microsoft signature. And there's another one that we talked about in the exam, which was Flame. Flame actually had a signature from Microsoft. And the reason that was is it turned out Microsoft, in their infinite wisdom, had put up a certificate authority, but not for signing certificates. It was an online certificate authority that was designed to give out certificates for licensing, specifically licensing something called terminal server, I think it was called. Terminal server or terminal services, and they would give out licenses. So a license server is basically just the same thing, but you would have to pay them money, and they would give you a certificate that lets you connect to a terminal services server for like 30 days or a year or whatever. And so they were using certificates to sign their license systems. But it turned out that the master public key for this thing was kind of, the thing that was above this certificate authority for the licensing server was also the same thing that was above their software signing CA. And it turned out, due to a flaw in the way the certificate chain was built, you could get one of these license certificates, and you could actually, in some cases, change some things around so it would look like a software signing certificate. But it actually turned out that they needed to do another cryptographic attack, which I mentioned, which was find a collision and a hash function to make this into a real attack. But the end result was they got a piece of software that looked like it was signed by Microsoft. Bad stuff happened. So these kind of certificates are a big deal. What else happened in the news? Yeah. Anyone? Yes.
Might be a little bit more political, but it turned out that large amounts of ultra-conservative entities on social media were Russian bots.
Yes. I don't really know what the lesson here is in that, but you can't trust people to be who they say they are, right? And one person can be a lot of people. So how do you actually stop that? Does anyone know what this is called, like in a computer science distributed system sense, when one person pretends to be a lot of different nodes, a lot of different people? It has a name. We might have mentioned it. Starts with S. Yeah, okay, so a Sybil attack, which is the closest I can find anything CS related that relates to this, right? So in a Sybil attack, you basically have one person pretend to be lots of nodes in a distributed system. It works fine. And Twitter, it's very hard to tell who is what. How do we stop Sybil attacks? How do we find out, who is actually a person? How do we limit this? Anyone have any techniques that we use in real systems? I don't know how to do it on Twitter. I have no idea how to do it on Twitter. But how would you do it in like another kind of system? How would you know that one identity is actually tied to a person? Yeah.
I know in certain countries they have it so that when you register for any kind of social media, you also have to put in like your, basically like your social security number or other kind of government tied identifier.
Okay, good. So in some countries, there's actually like a human authentication piece where you basically say, here's who I am, and this makes sure that things are like locked one person, unless someone defrauds them. But there's probably consequences for doing that. So you can do human authentication, but that requires human beings to verify it. So that works sometimes, doesn't work other times. Yes.
You can check by the MAC address, but again, he can just use a different computer.
Right. Okay. So you can use all kinds of identifiers, but most of these identifiers, like MAC,
Or he can also spoof it.
can be spoofable. So not so great. What else could you do? If you want to know one person is one person, what else could you do?
I know some kind of systems they issue computationally intensive challenges.
Good. Give me an example of such a system.
Or,
Okay. Tor. Give me another one.
Cryptocurrencies, like,
Bitcoin.
cryptocurrencies.
Bitcoin. Yeah.
Bitcoin.
Cryptocurrencies. Good. So cryptocurrencies solve this problem by basically saying, well, we don't care if you're one person. What we care is how much CPU power we have. So we're going to give you, in a system that requires basically voting, we're going to make you solve really hard puzzles. And the idea is, yeah, you can have one computer and you can pretend to be 1,000 people, but that you're still going to have the same amount of CPU power. So what that means is the voting power that you have, if we tie it to how many puzzles you can solve per second on your computer, then who cares? You can pretend to be 1,000 people, you can be one person. The actual amount of computation you have determines your voting weight anyway, so that doesn't help you. Sybil attacks don't help you in that setting. But what happens with things like Bitcoin that kind of undermine this idea? Like in practice, Bitcoin uses this system to decide who gets to choose the next block, and it's based on how much computational power you have. What happens?
But what if you have a different computer then?
If you have 2 computers, you get 2 votes. If you have 1,000 computers, you get 1,000 votes. So
Then
continue.
Okay, but that's not going to stop you from.
It's not going to stop you, but the idea is that hopefully you won't get too many people with big supercomputers. That's the theory.
But you do have people with big supercomputers.
You
right?
do have people with big
So
supercomputers.
that's an issue.
That is an issue. And more to the point, let's say we specify a particular puzzle. By the way, when I say something like puzzle, the Bitcoin puzzle is super easy, right? So the Bitcoin puzzle is literally, and I'm simplifying just a little, but it's literally compute a SHA-256 hash on some data. I won't get into what the data is right now. But you compute a SHA-256 hash on some data, and you win, let's call this T, you win if T expressed as an integer, so it's a 256-bit integer, is less than some constant that the network determines, right? So let's say that constant is very small, but you can basically adjust it so that the probability that if I do one hash on some data, I'm going to get a small enough output of this hash function is very low. I could make it 1 in a trillion, or I could make it 1 in a trillion trillion. I could make it as small as I want just by adjusting this constant. It's not really a constant, it's adjustable. Maybe we'll call it something like a difficulty level. Okay, so this is basically what Bitcoin does, and this difficulty has to adjust from time to time, so it's not really constant, but this is the idea. So let's say that, I don't know, let's say I've got a 1 in a million chance if I hash one piece of data, right? So then if I hash a million pieces of data that are all slightly different, I get a million shots at winning this puzzle. If I make it 1 in a trillion, now it'll take me, a trillion with expectation in order to get a solution that satisfies this equation. So basically, by adjusting this difficulty, this super simple puzzle is literally just a question of making somebody compute a lot of SHA-256 computations until they get one where the output satisfies this inequality. And then by adjusting that difficulty, you can make that very, very costly, requiring more and more computations. But what's happened in Bitcoin to kind of undermine the idea that like one CPU gives you a certain amount of computation? Right, so first, okay, so originally when Bitcoin launched, this was done using CPUs. And then later on, what happened? You said GPUs. What's a GPU?
It's basically a lot of cores.
Okay, good. So it's a graphical unit. Basically has a lot of different cores that can compute the same operation on multiple pieces of data at the same time. So it's really good at parallel computation. Graphics requires that, but it also turns out that you can use it for crypto. If you're doing stuff like this, you have 10,000 cores, you can do 10,000 hashes at the same time. And what's even better than a GPU?
PGA or ASIC.
Good, ASICs and FPGAs, but ASICs are cheaper. ASICs are application-specific integrated circuits. You can make one that is literally designed to solve the Bitcoin problem. And it can compute orders and orders of magnitude more hashes per second than a CPU or a GPU can at a fraction of the price. And so what's really happened is, although this was designed to kind of make sure that one computer got one vote, what's happened is, thanks to this optimization, people have actually kind of centralized a lot of the processing. And so now it's not really such a great system anymore. Just because this algorithm is not changed, it's relatively easy to game it by building ASICs. Okay, so Sybil attacks are just a hard problem, and nobody really has a great solution to these problems. But these are things you should know about. Somebody mentioned Tor. Why? Does anyone know how Tor works? Anyone give me a quick description? Tor is awesome. What does Tor do?
So Tor has a directory of available nodes, and the client that wants to communicate anonymously with its destination will select 3 nodes. There's an algorithm for it, roughly based on available bandwidth, and then from that directory it gets the public key for each node, and then it wraps its intended message, and it wraps it with the final node, and then the intermediate node, and then the first node, so that each node is able to unwrap its piece of the pie and see the previous link in the chain and the next link in the chain, but nobody in that chain can see the whole way from the sender to the receiver.
Good. So Tor, basically, we start with a collection of nodes all over the world, and what we do before we get to the crypto is we try to establish a path. Usually it's about 3 long. So we'll do something. I want to connect to some website, but I don't want the website to know who I am or where I'm coming from. So I'll have 1, 2, and 3 connections through these random volunteer nodes, and they're just relaying my traffic. That's all they're doing. Okay, but the problem here, so from the website's point of view, the connection initiates from this point. So we know they see this person and not me. Okay, and then from this guy's point of view, well, he sees that the connection is going out to the website, and he sees the person before him who's actually making the connection, but he doesn't know who I am still. And of course, finally, you've got this person, which we call a guard node. And this guard node actually does talk to me, knows my IP address, but on the flip side, doesn't know where the connection is going. So all they know is the next person in the chain. They don't necessarily know where this is all going. And we use layers of crypto to make sure that nobody can actually break into this. So what happens when I start out this connection, I will add 3 layers of crypto. Let's see, 1, 2, nope, 2 layers of crypto. Sorry about that.
You're missing a node in the middle. But
oh, am I missing a node?
Yeah.
I'm sorry. Yeah, you're right. I should have an extra node. That's missing. Yep. So let's add a 3rd node. Okay, now we have an actual third node, right? 1, 2, 3, good. And so what I will do is I will add 3 layers of crypto. This is going to be my 3 layers of crypto. And at each, oh, I think I need an extra line. So this is the actual connection, the data that I'm sending, and we wrapped it 3 times under 3 separate keys. When it arrives at this node, the outer layer of crypto will be ripped off, like ripping off the present, you know, like the paper from a present. What's inside will still be encrypted with an underlying layer of crypto. It goes onto here. Another layer of crypto gets ripped off. The final layer of crypto gets ripped off here. And what goes to the website is plain text. The idea being that if you're an attacker who is here and here, these connections still have very different data. Even if you're colluding, even if you're having 2 different people on different parts of the connection talk to each other, the data should look very different because of that encryption. They should not be able to correlate that they're seeing the same data. And this is the basic idea of Tor, is using crypto and lots of nodes to route your connections. Now, how does Sybil attacks screw this all? Yes?
So what is the encryption protocol that's being used? Is it similar to TLS, or is it?
They use a combination. So there's a TLS protocol, the actual TLS that runs on that first hop from your client to the first node. And then underneath that, they use Diffie-Hellman 3 separate times. You use Diffie-Hellman to connect. They have this kind of crazy Diffie-Hellman handshake to get a key established with this one, to get a key established with this one, and to get a key established with this one. And then the actual crypto, interestingly enough, is 3 layers of AES in counter mode. And I think there is a MAC, but only at the end. Why would you use 3 layers of AES in counter mode, actually? Any ideas? What's nice about layering counter mode 3 times? What might happen if you, what's good about counter mode? What is the one nice property? Let's say your goal is to preserve bandwidth. What is the one nice property?
Parallelizable.
It's parallelizable, good. But what about the bandwidth of AES counter mode? How much does the ciphertext size increase when you encrypt something with counter mode?
Just padding.
Yeah, you could have some padding at the end of it. And remember, in counter mode, if you start with a 0 key and you have like packet numbers included in the protocol, you can use those packet numbers as your counters. So you don't even get an IV. Like literally, if you encrypt something 3 times, you're not even adding 3 IVs. You're basically getting a ciphertext that doesn't grow no matter how many times you encrypt it. So that's why they chose counter mode. Anyway, so the long story short of this is that Sybil attacks are very, very bad for Tor, because the assumption here is that this person, called them A, this person B, and this person C are not colluding. But if it turns out that A, B, and C are actually the same person, those assumptions go out of the window, because that person would see all of your traffic from the start to the finish and would know everything about the connection. So these things kind of break down. Give me one other attack on Tor that would still be a real scary thing, even if not all 3 players are colluding. Let's say 2 of the players. Let's say A and C are colluding with each other. What other information might they use to attack the anonymity of a Tor connection? Yes?
You can do a timing attack to see who A is trying to connect to and see kind of what website you're trying to reach.
Good. So if they look closely, remember this is website data. If they look at a combination of the time that the person makes a connection, the me makes a connection to A, and the time that traffic arrives at the website, and they also do traffic analysis, they see, oh, big blob of data just came down from the website, and coincidentally, a big blob of data just came down from here. You can start doing what's called a correlation attack, where you can start to say, okay, even though I don't know what's going on in the middle, I'm pretty sure that these 2 connections are the same person. And now you've de-anonymized someone. And this is a big deal because about 2-3 years ago, a bunch of random Tor nodes appeared on the network. And they had all been spun up on Amazon EC2. They were just Tor nodes. Thousands and thousands of new Tor nodes appeared. And it took 4 or 5 months for the Tor project to notice that this had happened. And they were all controlled by one person. And it didn't mean that it was very low probability that person had enough nodes to control the entire circuit. But they did have enough nodes that some of the time when you made connections, they would control 2 different. They would control the A and the C on this path. And by using timing attacks and things like that, they could de-anonymize you. Does anyone know who these people were that did this? It was a big deal at the time, yes?
The CMU Software Engineering Institute.
Yes, an organization called US CERT, which is a bunch of people who do stuff for like the US government and law enforcement at CMU. They had basically they came up with a theoretical attack, which wasn't very interesting, but then they did it. Using a bunch of money, rented a bunch of Tor nodes, and actually implemented their attack. And what were they going after? Who were they specifically interested in de-anonymizing? There was one target that they liked above all others. Yeah.
Was this the Parrot Roberts?
Yes, they were trying to find the actual location of a website called Silk Road that was run by Dread Pirate Roberts, this guy who is not actually a pirate but was arrested recently. And the way that works, just one last feature of Tor, is that there's a second feature of Tor where the website itself can also be anonymous. And what happens is you take a middle node, let me see if I get this right, and you call that a rendezvous point. And to make a long story short, what you do is you have 3 more nodes to the actual website. So the idea now is instead of a 3-hop connection, I make a connection 3 hops to this location, the website makes an inbound connection 3 hops to this location, and now neither of us, if everything works right, should know. I shouldn't know where the website is actually located, and the website shouldn't know where I am located, and all of these darknet marketplaces use this hidden services feature of Tor. Yeah?
So does the rendezvous point handle plain text information?
No, it is encrypted. There's one extra layer of encryption that means all the data flowing through it is encrypted. There can be several rendezvous points and so on, but they don't actually see the data. But the basic operation of the system is it's 2 different connections that arrive at some central point. There are a lot of details to how you pick that central point, find that central point. But this is the current data, roughly speaking. Okay, good. So this whole system was basically attacked using a Sybil attack, where somebody made lots of nodes that were all just the same person, moved lots of traffic through, and eventually got a lot of information. We don't know. We just know that the guy was arrested. We don't know all the details in between. So anyway, these are interesting things you can do with crypto. It's not exactly what we're going to talk about today. 2 things I should talk quickly about: logistics stuff and housekeeping. Any questions about this random discussion? And then I want to cover something off topic, and we're going to start talking about provable security. Oh gosh, go away. Can't make that thing go away. Hang on a second. Somebody told me that this little adapter I have, this dongle, is basically a little iOS device, and that's why it needs an update so badly. It's got its own operating system, and that totally freaks me out. This is smart. Okay, quick housekeeping stuff. All right, so I put out a reading list. It's just a few selected papers on Piazza. I did it this morning. You should see it. Read those papers. There may be more coming, but this is kind of essential papers from the syllabus you should read. The final, people have been asking about this. The final is going to be on the last day of class. It's going to be a 1 hour, 15-minute final. Good. Projects. I know you guys have been diligently selecting your projects and your team. And you all have this all worked out. I didn't really think to put any pressure on you to actually do this in a timely fashion. I feel like if I don't put some pressure on you to do this in a timely fashion, it will be December 6th, and you guys will be still picking your project. So please, get on it. This project is a big chunk of the grade, and I want you guys to do a good job. So I'm going to say Wednesday, and that's generous. Please try to get it before that. Give me a short write-up. It could be a half a page if it's succinct and explains what the deliverable is, what you're doing, and most importantly, who your team is, which will be like 3 people if you want, and gives me an idea of what you guys want to do, and says, here is what we're going to do at the end. And the 3 kinds of deliverables I'm hoping to get, unless you blow me away with some alternatives, are an amazing presentation that really is great, an actual piece of software that you wrote, and these are not exclusive, or a really good write-up paper on one of these topics that covers it. So it depends on what the topic is. So that is what I need, and I will put up a Blackboard. I didn't actually do it before class, but I will put up a Blackboard middle assignment for you guys to submit to. So put something in. You do not need to have if you have a team of 3, you don't need to submit 3 copies of it. It's not graded. I just need 1 copy from one team member that lists the other team members. Okay? Good. I think that was all my housekeeping stuff. Any questions about the project that you guys are going to do awesome on? Yes.
When is it due?
The write-up?
No, the final one.
The final project is going to be due basically by the end of class. I'm willing to, if it's great, maybe we can extend to the final day of class, the final normal scheduled final. But it's really, so we've got about a month, maybe even a little less than a month. So we really got to kind of get moving, and we'll see what happens with that. You guys have had lots of time to think about it. Hopefully you've thought of great stuff, and we'll see what happens. Feel free to talk to me, come talk to me, and we'll see if you have ideas that are a little weird, or talk to Alicia. And we'll try to figure out, whether those work. Let's see. Okay. So last time we talked about protocols, and we talked about a bunch of different ways they can break down. We talked about specific examples. Two of the examples, SSL TLS, and there is a reading that talked about the SSL 3.0 protocol. Covers a lot of the things we talked about in class, so do read it, it's very important. We talked about a protocol for cordless telephony called DECT. Also has a lot of issues, turn out to be the same issues that occur in GSM phones. And I just want to quickly walk you guys through. Who can tell me, I don't know if we covered these all explicitly, so I figure we should. What is a replay attack on a protocol?
It's when you replay part of the exchange in order to confuse one side or the other as to which stage that they're at in the handshake
Good.
or in the communication.
Very good. So if there's a protocol going on and I'm able to eavesdrop and record communications between two parties who are not me, and I'm able to, let's say, replay by recording, I can replay a message either to the person it was going to later a second time, that's a replay attack. And in a lot of cases, those kind of things can be very powerful. Where I'm just in the middle, I'm able to replay. What's a reflection attack? I don't know if we talked about that one. Yeah.
Seeing a message that one side sent and sending it right back to.
Good. Give me an example of where that might happen and that could be bad. Why would I want to reflect something back to you? Any ideas? Yes.
If I could trick you to answer the question for me.
That's a great idea. Let me try to make up a protocol that might be subject to a reflection attack. And this is kind of off the cuff, so it's not going to be great. But let's say we have a protocol where two parties agree on a key K, A and B, and I'm in the middle. Let's say they have K here, K here, and I'm the man in the middle, whatever, right here in the middle. And so Alice sends an encrypted message, it might even be MAC'd, some message M to Bob. Okay, I am a man-in-the-middle attacker, so I'm going to capture this message, and I'm going to turn it around. This is me, by the way. And I'm going to send it back to Alice. Well, if Alice expects the messages coming from Bob to be encrypted with this key K, then Alice will look at this message. Maybe it's even MAC'd. Alice might not know that this was her own message just being bounced back at her. Maybe the message says, delete all files, which, is something Alice really wants Bob to do. But maybe the message, when replayed to Alice, tells Alice to delete all files. It's correctly MAC'd, it's correctly encrypted. Alice decrypts it with her shared key, and wham, she deletes all her own files. Okay, this is a really stupid example of a thing that might happen, but in real protocols, bad stuff like this can happen as well. So you can run into these kind of reflection attacks. You raising your hand? Oh, okay. Yeah, so these reflection attacks can do bad stuff. It really depends on what the actual protocol is that's going on. Okay, in the Clipper chip, there were a bunch of reflection attacks that basically allowed you to do terrible stuff. Okay, the last one is a downgrade attack. Hopefully somebody can tell me what that is. Talked about downgrade, and we talked about other related to downgrade kinds of attacks a bunch over the last two classes, so hopefully somebody can remember.
Well, you basically roll back to the previous version.
Good. We also talked about rollback attacks. Do you have another example? Or?
No.
Okay. Yeah, so downgrade attacks where I say, you are running for protocol version 3, but I really know there's a bug in protocol version 2. How do I convince you to go to a weaker version of the protocol so I can then attack, or it's also called a rollback attack in some cases. How do I get you into a weaker protocol which I actually can attack? So these things are really fundamental classes of attacks, and they can really break stuff very badly. Two things. I want to show you an example of a real protocol that actually is kind of broken due to a bunch of these things. And then I want to distract us for a second because I want to talk about symmetric encryption quickly. Okay, here is this crazy looking protocol, which you can be very glad that I'm never going to give you on an exam. It's an example of a thing called the HDCP version 2 protocol. Okay, HDCP stands for High Definition Content Protection or something. I don't remember what it's exactly. Basically, this is a protocol that runs between your phone and your TV. If you want to do something like project a movie from your phone onto the TV, like a Samsung TV, you're going to run a protocol like this where your phone is going to communicate with your TV, and it's going to actually create an encrypted channel And all of the data you're sending to your TV is going to be encrypted. Why are we going to do this? Because the people who make movies are stupid, and they think lots of people are going to break the movies or pirate the movies by somehow like intercepting unencrypted content over these wireless channels and do bad stuff to you. So they want everything that goes over the wire or wireless connection to be encrypted. Makes perfect sense. Okay, this protocol is very badly specified, but roughly speaking, I'm going to sort of show you the important parts. Okay, so this protocol, we assume that there is a public key that the TV has. Let me see if I can simplify it just a tiny bit. Okay, so we have no eraser here. Okay, so we have a protocol. Well, since I've already got A and B here, let's say A is my iPhone. Okay, and B is my Samsung TV. Okay, and we're going to assume right off the bat that there is a certificate installed on my Samsung TV. And most importantly, this has a public key for my TV. As crazy as this sounds, this is a real thing that people expect will happen. And if you look at this kind of message here, it says the person on the left, the transmitter, generates K sub M. And encrypts K sub M with KPub RX, which is to say, this iPhone over here generates K sub M and sends over some kind of public key encryption, oops, encrypt, under PK K sub M. All right, what's going to happen at the end of this? What do you expect is going to happen? Well, now they share a key. So everything should be good. Now they should be able to communicate using encrypted messages. If I'm a man-in-the-middle attacker, can I break this protocol? What do you see? What could happen here that could be bad? Just looking at this protocol. Really, this is the entire stupid protocol, where you have somebody generate a session key KM, encrypt it to the Samsung TV's public key, and then later on, presumably, we're going to communicate using K sub M. Oops. Okay, what kinds of attacks do you see immediately? Yes?
Well, you can generate your own case of them.
Anybody can generate their own K sub M, that's true, and I can talk to the TV. Unfortunately, maybe that's useful, maybe that would be useful in some other part of this attack or the attack, but talking to the TV isn't forbidden. Decrypting, the latest version of Guardians of the Galaxy, that is what we want to prevent, and that comes from the iPhone. So I don't know if this will help us, but it could be useful. Yes?
Generate your own PK. Give the iPhone their own certificate.
Good. We could do that. However, there is a certificate, and it turns out that certificate has to be signed by some licensing authority. And so the iPhone will not just accept any public key. It has to be signed public key, signed by the HTTP licensing authority people. So I can't do that attack, but that would be good. Does that make sense? Okay. What else do you see? Yeah.
Breaking into the TV.
Okay, breaking into the TV probably works good. Breaking into the iPhone probably totally works. The assumption we're working under here is that the best way to attack this is on the wire, not by hacking into the TV. If you can hack into the TV, I bet that would work. What else could you do? Well, what if I just record the movie, the encrypted movie, going over the wire? I record that encrypted version of K sub M, and I just later on, let's say all I want to do is replay them to the TV. I could do that. Nothing would stop me from replaying the movie 10 times to the TV. It's a very lame attack. I don't know why you would want to do that, but it could work, right? So now I can replay the same movie 10 times without actually having the iPhone present. So you could come to my house, play the movie once, I'll record it, and now I have a permanent recording of this stupid movie. Like, this is an attack. You can see there's nothing in there to guarantee freshness. That's something that's obviously missing. Okay, let me add one detail. Right, so public key encryption for TVs is kind of expensive. And so the people who designed this protocol did not want to do more of it than they thought they had to. So they added an extra mechanism. Let me see if I can find this here. Okay, the very last thing the TV does after it's checked that the whole connection is working right is it actually, before it communicates, starts communicating with KM, it sends back. This part's a little weird. It has its own key, which is called K, God, it kills me that they have all these different names. KH, don't ask me why. And it encrypts using a symmetric encryption scheme, so pretty fast. Using its KH key, it encrypts K sub M.
Could you just have a timestamp?
Just to do freshness, if you had synchronized clocks, you could do that. Okay, but this is a different mechanism. Why we have this? Let's say this is an AES key, KH. When we finish, once we've established a key, K sub M, using public key encryption, the TV will now encrypt a copy of that session key, K sub M, and send it back to your phone, which will store it for the next time you connect to the TV. Why would it do that?
Because the session will expire, and as a result, you won't be able to replay it in the same session.
Okay, but you could always just start the whole public key protocol again with a new K sub M. Why would you store a copy of K sub M on the iPhone? What is possibly being achieved there? Yes?
It's just so you don't have to go through the DMG.
Yeah, the whole idea here, it's just an efficiency boost. The idea is the first time you connect to a TV, you have to do this whole rigmarole of, encrypting it, generating a K sub M, encrypting it with a public key, sending it over. And then the idea is once you've done that, all that extra work, now the TV will very efficiently use its local key to encrypt a copy of K sub M, send it to your iPhone, and your iPhone will send that copy back to the TV the next time it connects. And there's actually a message in here. Let me see where that shows up. I'm not quite sure where it does show up. It's in here somewhere. Transmit encrypted K sub M, I think. Maybe it's on the next slide. Shoot. There is a message. Trust me, there is a message where it does. You can actually send back, when you want to make a faster connection to the TV, you'll basically send back this stored ciphertext instead of doing the public key thing. That's the idea. Okay, great. What could be the problem here? Well, let's look closer. When I said we compute the encryption of K sub M using some kind of fast symmetric encryption, what does that actually mean? Well, the actual encryption looks like this. This is a little weird. What is going on here? Okay, so we have an encryption. We have this KH, that's the key that we're going to encrypt under, goes into AES. We have K sub M, that's down here being XORed into the output of what comes out of AES. And then we have this thing here called M. M, let's go back and see if we can find M. Hold on real quick. M is a value that is sent from the phone. So the phone sends M. It doesn't show up on the slide, but the phone gets to pick M. The phone gets to pick K sub M the first time it sends over this encrypted ciphertext, and this is the resulting encryption, encrypted K sub M. What's this mode of operation we're looking at? Looks a lot like counter mode, doesn't it? Right? So we're saying encrypt under counter mode. Let's say counter encrypt under K sub H, KH, KM, with counter M. What do we know about counter mode? What is the one thing we know about counter mode that you should never do? Where does counter mode get bad? Yes.
Like repeat counters.
Good. What happens when you repeat counters?
You can XOR to plain text.
Okay, that sounds pretty bad. What else do we know about counter mode? What about encryption and decryption? How are they related in counter mode?
The same.
They're the same. So what does that mean here? Let's think about this. So if I were to send to the TV, if I were to intercept this encrypted KM from one legitimate handshake, and then I were to make another handshake where I can choose, in this new handshake, I can choose a whole new KM of my choice. And instead of passing in the same KM, I would pass in, let's say I take that encrypted KM that I intercepted the first time around, and I feed that in as the KM to be encrypted. And I make sure I specify the same counter because I get to choose that for whatever reason. What has just happened? What is the result of this going to be? Right, so I steal an encrypted ciphertext, and I send that in as the plain text to be encrypted. Okay, let's work this out because I'm not sure that this is totally. Remember, we have so we'll say E is the AES encryption. Okay, so we have E of K and what? It's M XORed with K sub M, and so we'll call that the encrypted value. And remember, we can intercept that. We can let a phone connect to a TV. We can intercept this encrypted value. And now I can make another connection. Okay, in this new connection, I also specify the same M. I know it's going to be encrypted with the same key. Okay? And what's going to happen? Well, that's going to be encrypted with the actual plain text I send. And so I send in the encrypted value I got on the first handshake. Okay, let's write this out. Okay, so we'll write this out. The encrypted value is equal to E of K, comma M, XORed with K sub M. When you look at this and you try to solve, what do you see? Well, you see this will cancel out with this, and the result is what gets sent back to you with the supposedly encrypted value on the second handshake is literally this K sub M value. And now you have the master key that this handshake is agreeing to. And so as a result of this, you can actually now decrypt any past or future handshake made between this iPhone and this TV. You can get the data from Guardians of the Galaxy. You can do whatever you want. Maybe this is a big deal, maybe it isn't. But this is an example of how people can make really, really stupid decisions in protocols. How do you fix this? How do you fix this? How do you make this so this is not vulnerable? What happened here? Yes?
Did the TV set the counter?
Very good. So we are expecting this to be an encryption scheme, right? We expected when we encrypted this KM, it would be securely encrypted. But we know that counter mode is a secure encryption scheme, but not when the bad guy gets to pick the counter. And so if we just made the TV pick a counter and make sure that counter is unique, we would have been fine. But we let the adversary do it, and this is an example of bad stuff that can happen to you when you let the adversary choose your counter that you're going to encrypt under. There's a lot of other bad stuff that can happen. Okay, good. Before I move on to provable security, I want to talk about one other kind of random issue. I'll put these slides up, and you can actually look at this protocol. There's even a blog post about it that kind of talks about the silliness of this. Many protocols suffer from these kind of problems. You go out to build a protocol, it all seems like it's going to make sense, and then you screw up this one little thing, and everything you've done becomes insecure. This is why I'm obsessed with protocols, even though I know you're all very bored by them. Okay, one second. So I want to ask a question. Let's say we're using DES. This is a symmetric encryption question. Okay, so we're using DES. How big is the key for DES? I don't remember.
56 bits.
Is 56 bits a good key size? No. So what do we do if we have to use DES, but we want to use a larger key? What's that? Yes.
Can we do 6 DESs in a row?
Okay, good. Let's start with 2, just to make life easy. Okay, 6 sounds awesome, but wait, I don't need to keep that big. Let's go with 2. Okay, 2 DES keys. So my idea is this is the DES encryption, by the way, DES N. And so what I'm going to do, let's not worry about what mode of operation I'm using. Let's say I just want to encipher a value M. I'm going to pick a value K1 for the first instance of DES. I'm going to take the output of this. I'm going to have another value K2 for the second instance of DES. And I'm going to hope that I get a ciphertext out of this twice. Does anyone see any problems with this idea? Seems like it's a pretty straightforward way. How big, if you look at the combination of the 2 keys I'm using, how much key material do I now have in my DES cipher? My double DES cipher. What do you see? What's that?
Just 112, right?
Yeah, it looks like 112 bits. So 112 is a lot better than 56. So just by using DES twice, we've apparently doubled the security strength of DES. Seems like a good deal. Have we actually doubled the security strength of DES? Will it take me 2 to the 111 on average operations to decrypt, to brute force decrypt this double DES ciphertext? Who wants to bet?
I think it'd be 2 to 57.
Good, why?
I mean, you're decrypting one, then decrypting the other, so it's 2 to 56 times 2.
I like your intuition, but I'm not quite sure how to do the thing you're telling me to do. Give me a concrete attack. Yes.
Well, you still end up. Isn't there only one? And still, yes, there are 2 transformations, but it still only is doing. Still only has 2 transformations in the total, right? So you end up having these 2 maps, but it still maps to the same side.
So I'm not. I understand kind of what you're getting to. I mean, there actually has been some work. If it was the case, and this is kind of a not very sort of esoteric, if DES was a group, meaning that if doing DES twice with two different keys was somehow equivalent to doing DES once with a different key, which could happen in some kind of algebraically designed ciphers, then it would be the case that you would not be strengthening the cipher at all. Here we're going to assume that DES is not. DES is actually not a group. But here we're going to assume that DES is like a perfect random ideal cipher. It does not have that property. So these two instances of DES with different keys should not somehow coalesce down to one with like a third key. Okay, but does anyone see an attack? Let me be a little more concrete about what I mean by an attack. I'm going to give you, just to make life easy, I'm going to give you the encryption of a known plain text, or even a chosen plain text. I'm going to say, let's say your plain text, I'm going to make it easy, it's just going to be a bunch of zeros, and I'm going to pass it through this DES construction, and I'm going to give you a ciphertext. Okay, what is the generic, if you have all the time in the world, way that you can figure out what the key to a cipher is if I gave you this plain text and this ciphertext? You would brute force. You would try every possible key. In DES, that would be 2 to the 56, which you could probably do in a reasonable amount of time. Eventually, you would get, you would encrypt, you do for I equals 0 to, 2 to the 56 minus 1. You would encrypt under I the plain text, and you would check to see if that was equal to the ciphertext, and if they found one that was a match, you'd be good. Let's leave aside the fact that DES is a little, the size of the block is a little smaller than the key, so you might get some collisions. Let's not worry about that detail for now. So let's just go with this. This makes sense? This is how you do a brute force attack, try every possible key. So we know we could do this. We could try every possible K1 and K2, which would take us on average 2 to the 111 operations, or 2 to the 112 in the worst case. But is there a faster way to do this? If I give you a P, and I give you a C, is there a faster way to do this? Is there an attack that would let me get this in 2 to the 56 like you would, or 2 to the 57 like you've hypothesized? What could I do? Let's say I have storage. Can we do something with storage?
A rainbow table?
Yeah, but not with a rainbow table.
Okay.
Let's just say a regular old table. Okay, I'm going to give you a hint. Let's say we start by building a massive table for every possible DES key. Remember, not the double DES keys, just the 56-bit DES keys. How big is that table going to be in bytes? Can anyone quickly work this out? Okay, we've got how many DES keys? Okay, so we've got a table. Well, we've got 2 to the 56 possible keys.
Right.
Okay.
Oh, yeah.
So it's 8 bytes times 2 to the 56, so that's another factor of 3, so it would be 2 to the 59 bytes or something like that. So this is basically an entry for each key that DES has. We would end up with an entry that has the encryption of our fixed plaintext P under that key. So we'd end up with, for this fixed plaintext, and I said the plaintext is 0, let's make life easy. Okay, so we have an encryption of 0 using each of the 2 to the 56 DES keys. Yes?
That's half an exabyte.
Is it? Whatever. We got a lot of space, okay? We're fine. We just buy a lot of hard drives. Or we wait 10 years and we buy more hard drives. Okay. So we've got this table. It's about 2 to the 56 or a little bit more than 2 to the 56 bytes in size. Now that you've built this table, is there anything that you see that could happen here that would let us do an attack against this double DES more quickly? What do you think could happen? We first look up C. Okay, so the problem here is maybe that would work. I'm not quite sure. But the assumption would be that if this middle plaintext was 0, then yes, looking up C would work, because if we found C, then we'd know we found the right key to get here. The problem is, what we have is 0 up here. And so I don't know that that strategy would work. I like where you're going with it, but I don't think it would quite work.
Do we get to view the intermediate value between the two
Nope,
tests?
nope. You got a plain text, which is this P, which we just said was 0 from the top here, and you got the ciphertext that is down here. You have no idea what's going on inside of those two calls to DES. You just got the end result of the double DES. But you have this table that you made yourself. Can you use this table in some way? Okay, second hint. No. K1 and K2 were chosen randomly by the person we're trying to attack. We can't fix the keys.
So we said we can eventually find an encryption is to go to ciphertext with the from 0.
I like the idea. However, the problem is we've just got this table. And the table was just for single des. And so we have the problem is, yes, if we could find an encryption where the ciphertext gives you 0, okay, I think, are you saying, so where are we starting? Where is this encryption? Is it here or is it here?
In the middle.
Ah, okay, good.
So if we can find a single plain ciphertext that where the plain text will give you 0, then we can set the K1 to the K that we have it over there such that the first output is a 0.
Good.
And then we can use the table lookup to find one where we met the result to C.
So I think you've pretty much got it. I'm going to rephrase it slightly differently. So we have this C. This is a given, part of our attack. So we know that there's some value K2. It's a 56-bit key that goes from C back to here. So for I equals 0 to 2 to the 56 minus 1, we can basically try every possible value of K2. And we go back to here. That gives us some value, which I'm going to call X. Okay, what do we do when we try to get that value X? Well, we have a table. Okay? We take X and we look it up in our table. And our table consists of all values that if you decrypt them with a particular key, will give us 0. Okay, so basically we have to do one table lookup on X. If X appears in our table, right, that means whatever key it was associated with must be K1, or probably is K1. Does that make sense? So we do 2 to the 56 operations here to try to guess K2. And then we multiply that by basically one table lookup each until we find one that gets us, gets a match in our table and gets us back to 0. And so now we've basically done 2 to the 56 total operations here, plus how much time did it take us to build our table? How much work did it take us to build our table? 2 to the 56 operations, right? 2 to the 56 to build our table, plus, plus 2 to the 56 times whatever it takes to look something up in a table, which is logarithmic and very fast. It's an efficient database. And so basically what we've shown is if you have enough storage, double des is not 2 to the 112 or 2 to the 111 operations to brute force attack. It is actually 2 to the 57 or so, which matches your intuition. And this thing that I just described has a name. It's called a meet in the middle attack. And the idea is that you just basically find the thing in the middle and use this table to get yourself the rest of the way. So these meet in the middle attacks are really interesting. Now, you guys know that there is a thing called triple des. And what is triple des? We talked about it early on in the class.
It uses three 64-bit keys or three 56-bit keys, and it encrypts with the first one, decrypts with the second one, and then encrypts, I think, again with the third one.
Okay.
It might have the details slightly wrong, but it gives you too many points of comparison to effectively do what you're talking about.
How secure is triple des? Isn't it secure? You just described it as having 3 keys of size 56 bits each. How many bytes, how many bits of key is that combined? What's 3 times 56?
168.
Good. So the question is triple des actually 168 bits equivalent to a 168-bit cipher? Is it equivalent to a 112-bit cipher? Or is it even less than that? And I'm not going to say the answer because I want to leave that question open for you guys. But it turns out that the answers are similar and maybe even related to the question of double des. These ciphers, these cascade ciphers, are not actually as secure as you think they are because of attacks like the meet in the middle attack. Now maybe these aren't really feasible, but these are real attacks. All right, sorry, I wanted to get that one off my chest, but do think about that a little more because it's a great question to ask you on a future homework or anything. Okay. Good. So today I want to, in the last bit of today that we have, I want to start talking about the area of provable security. Okay, so we've actually talked about provable security once in this class, we talked about one very, very important, very old result relating to provable security, which was related to this idea of information theoretic security. And you remember the construction we talked about was the one-time pad, okay, so which was invented by Vernon and Maubourne back in the 20s or teens or something like that. It was later systematized by a guy named Claude Shannon. And the one-time pad security proof, I hope you guys remember the intuition of this. The idea is that if I give you a ciphertext that has been correctly and honestly encrypted with a real one-time pad, meaning it's been XORed with a string of a key that is as long as the message and is perfectly random, then no matter how much time you spend brute forcing the key on that message, you're never going to get any useful information. Because in fact, for every possible key you could try, there exists, basically there exists one key for every possible plain text. So in other words, when you do the brute force, you're going to get every possible plain text, which means you're going to get no information about what the actual plain text is. That is the one that's encrypted in this. And every key is equally likely, so there's just no information here at all. And so we can actually write an information theoretic proof very simply. It basically looks like this. So provable security did not actually start, it did not start in the 70s, the 80s when people started doing modern crypto. It's actually much, much older. So this is great. Information theoretic security is secure against any amount of effort. If people build big computing rigs and they power them with fusion power, still not going to let us crack one-time pads. No special assumptions are needed. We're pretty much done. Just the idea that you're going to do things right. The disadvantage of the one-time pad is it's really, really inefficient. If you go around encrypting things with one-time pads, and by the way, every now and then you will run into a product that actually tries to encrypt things with one-time pads. And these things are almost always terrible. They're terrible for two reasons. Either they require you to carry around like gigabytes of one-time pad material and like walk to your friend's house or fly around the world and deliver gigabytes of one-time pad keys to your friend, which sucks. Or they will come up with a very, very clever hack. And they'll say, in order to save space, we found a way to compress the one-time pads and make them a lot smaller. And usually their compression is something like, use AES in counter mode. And then we can make the one-time pad keys like 16 bytes long. And we just generate lots of one-time pads with that. What have they just invented? Well, that's not a one-time pad. That's AES in counter mode. The key size is really only 2 to the 128 in that. It is not a one-time pad. So all of these systems that come out there really suck. And the only people who really use one-time pads in practice are basically spies who use them to communicate with people all over the world, where it's basically worth it to send one-time pads out with your spies. It's not worth it anywhere else. So in practice, when we build modern cryptographic systems, we don't rely on information theoretic security most of the time. We rely on something else that's called computational security, also known as complexity theoretic security. And the idea here is that we assume that our adversary has limited computing power. Okay, so there is some hard problem, and by hard we mean that the problem could be solved, but it would take a large number of computational steps to do this. And the kind of assumptions that we come up with that kind of meet that are things like the RSA problem. We know the RSA problem is solvable. You can factor large numbers if you take long enough to do that. You can solve RSA, but we don't think you can do it fast. Similarly, AES and DES, as best we know, these ciphers that we built, unless you do brute force key search, you can't really get a fast decryption of them. All these modern algorithms and stuff. So we can show, we know they can be broken with enough effort, but we basically say that kind of effort is not practical. Okay, so we typically, when we talk about these proofs, we have to invoke something that we call a hardness assumption or a complexity theoretic assumption, or a complexity assumption. Okay, so we've talked about a few of these. The RSA assumption is a very well-defined example of a hardness assumption. Discrete logarithm we talked about, also a good one, factoring and so on. When it comes to things like block ciphers, we use much stronger assumptions. The idea that AES is a secure block cipher, which is a pseudorandom permutation. It's really unlikely that somebody's going to ever prove that. Somebody might someday prove that factoring is fundamentally hard to do in polynomial time. We don't know. Maybe they'll prove it's not hard. We don't know. But we at least hold that hope that some of these mathematical problems, there exist proofs of some statement or another. Things like AES being secure, we don't really know if that's possible, but we like to make the assumption anyway sometimes because it helps us prove it. Okay? So here's kind of the example of what this looks like. I probably even showed this stupid diagram before. But typically we have the idea where we have operations that have to be easy. RSA encryption has to be easy, meaning this has to be pretty fast. RSA decryption has to be pretty fast. But things like extracting the message or the key from an RSA encryption have to be very hard. We want our adversary's job, without knowing the keys or trapdoors, to be very, very difficult. The easy part is just as important as the hard here, right? If we have an encryption scheme that's very hard to break, but takes 10 million years to encrypt a message, not a good example. We want the encryption and the decryption to be fast and the attacks to be slow, okay? So we actually want to go one step beyond just saying this is difficult. We really want to claim, we want to hope, that there is no efficient algorithm that computes whatever it is that we need to compute to attack this encryption scheme. So why do we focus so much on provable security? Well, one of the problems we have is that building ciphers and analyzing ciphers is very hard. We had the AES computation a few years ago. It lasted several years. There was something like a dozen candidates. Everybody fought it out. There was a big shootout. And eventually we got, one cipher. So doing that over and over for every new kind of system that we want to build is just not going to work. What we really want to do is we want to agree on a small number of hard mathematical problems that everybody is willing to focus on and really try to break and hope that they aren't broken. And then we try to build schemes that can be reduced to the hardness of those assumptions. So we don't have to recertify every scheme basically from scratch and try every possible attack. Okay, so this is the advantage of kind of thinking about computational security and doing security proofs. The disadvantage is, unfortunately, as nice as this sounds, we don't even know if complexity theoretic security is actually a thing that can exist in the universe. Anyone tell me why that is? Like basically what I'm saying is all of crypto that we use today may be bunk. It's a very strong statement to make. Can anyone give me a reason why that may be the case? And don't say quantum computers. Nothing to do with quantum computers. Yes?
Is that like key for that key?
Good. The question is, do we live in a universe, and I'll get to this in a second, do we live in a universe where these kinds of asymmetries are possible, where there are problems that are basically easy to compute in one direction, but very hard to undo? This is the big question. It's related to P and NP. We'll come back to that in a second. Okay? So one-way functions. Let me describe what one-way functions are. Okay? So one-way functions are kind of the foundation of crypto, at least symmetric key crypto, is the assumption that there exist these functions that can be computed easily in one way. Let me give you a slightly better definition. Okay, we say that f is a one-way function if computing f on x for all x is efficient. And I'll be a little bit vague about what efficient is, but typically in computer science, we'll define it as being, you can do this in a polynomial number of time steps in a Turing machine. Okay, it's efficient. Okay, but given, let's call this G equals f of x for random x, there is no efficient algorithm that finds x. So there may be inefficient algorithms that take an exponential number of time steps, but not necessarily efficient polynomial time ones. Okay, so what's an example that the universe gives for a one-way function? Okay, what's a real-world physical example of a one-way function?
Hash functions.
Okay, but that's a computer example. I actually want something you can touch and feel. Yes.
What about a semiconductor?
Okay, go further.
Well, a semiconductor, you can really only send current through one
In
way.
one, okay, fair enough. But I'm talking about things. I'm thinking about things that are easy to transform. Ah, good. Okay, that's the example I was hoping for. It's very easy for me to take something and destroy it. I can light something on fire and I get ashes. I can take those ashes, I can grind them up, I can dump them into the ocean. Very, very hard for you, we think, to go into the ocean, to get all of those ashes, molecules I've spread out all over the place, put them back together and undo the combustion and get back to that original piece of paper. The universe just seems to kind of not like certain types of transform in the way that it likes others. Now we don't know. Maybe it's possible in the universe there are everything we do is reversible, but we do know that some things in the universe seem somewhat easier in one direction than the other.
So you're going for more of like a thermodynamics argument on that.
I'm not going to make any argument on that. We could be wrong. Yes, it could be
I
that.
think that that's like, that's what you're going for there, is the second law of thermodynamics. that
Yeah,
you-
is it entropy and crypto somehow? And this is just a metaphor. It's not a real argument about crypto. But yeah, we like to believe that the same kind of things can happen in computation. That there are computations that can go one way very easily, and not as easily in the other direction. Okay. Okay. So this actually tells us something really interesting. Okay. There's a very well-known result that says if these crazy one-way function things exist, then it has to be the case we live in a universe where the complexity class P does not equal the complexity class NP. Okay, so this basically would tell us if crypto is possible, then we have an answer to the P does not equal NP problem. The reverse implication is a little muddier, but this way we know. Okay, so this is a huge open question in computer science, and sadly we don't know what the answer is. What is the general consensus on the PNP question among complexity theorists, though? Anyone tell me?
Not equal.
Right, so we believe that P does not equal NP, which means crypto is possible. Doesn't necessarily mean that, this is right. Tomorrow somebody could publish a paper showing us and proving to us that P equals NP, and then we'd be screwed. And crypto would just, well, not be done, but we'd be in very, very bad shape. Yes?
I think P equals NP is very much in the same boat as the action of choice, where we are pretty sure it's right, and we just assume it is because there's no reason not to.
Well, we have no real evidence that it's not. And we assume, it's also very beneficial to us here that we can assume this, yeah. But nobody's actually proven it either way, and it's a big open question. Go ahead and become a complexity theorist and prove it and win $1 million and other things that are probably more valuable than $1 million. What's that?
How do you do crypto if P equals NP?
That's a really good question. So what does it mean if P actually equals NP? Well, it doesn't necessarily mean that you can't build cryptographic algorithms in some way, right? So remember, when we say that, what it would mean is that one-way functions don't exist. It would mean for every function you could give, there would be an efficient algorithm that could invert the one-way function. So let's say this is a hash function. It would mean you could never have a pre-image resistant hash function because there would always be an efficient algorithm that could go backwards and invert the hash function, right? So that would be the implication. Now, there's a difference, though, between the word efficient, as complexity theorists use it, and efficient in the same way that actual human beings would use it. So, for example, it might be the case that the algorithm is polynomial time for inverting a hash function, but still takes 1 billion years on every computer on Earth simultaneously. So we could end up with these things where there is, a polynomial relationship between the difficulty of inverting and going one way. So one-way functions don't exist, but we can still kind of like limp on with some sort of crypto. The other possibility, we would always keep information theoretic crypto, so things like one-time pads would keep existing. But public key encryption would be not good. It would be a very bad world to live in. In fact, there's this really great paper by, I can't pronounce his name, Paglazio, anyone know how to pronounce his name? It's a great paper, I should post it to the Piazza. It basically talks about the different worlds we might live in. And basically it lays out these different worlds. Some of them have P equal NP, some have P doesn't equal NP. But there are even more worlds. Some worlds where P does not equal NP, but like symmetric crypto can exist and public key crypto can't. And other worlds where like both can exist and P doesn't equal NP. So there's actually a lot of kind of muddy different shades of gray in here that I'm like looping over. But for now, we like to believe that P does not equal NP. If we're cryptographers, we like to believe that one-way functions exist, and we just don't think about it very much beyond that, because if we do, bad stuff happens. Which brings me to the next thing. We're making assumptions. This is what we're doing when we talk about provable security. And the strength of an assumption goes up as it gets more specific, typically. So P does not equal NP, that seems like a very strong assumption already to start, but it's actually pretty weak. And weak is good. It gets stronger as we go on. Okay, so P does not equal NP. Let's assume that exists. Well, let's say trapdoor one-way permutations exist. The trapdoor one-way permutation is a class of things of which RSA we would like it to be a member. It's a permutation, it's a function where you can go one way, like RSA, but there is a trapdoor, a secret key that lets you go back the other way, which perfectly describes RSA. Okay, the existence of trapdoor one-way permutations is still a weaker assumption than the idea that RSA itself is actually a trapdoor one-way permutation. And why is it weaker? Why is trapdoor OWPs weaker than RSA? What does that mean when I say something is weaker?
The bottom one requires all the previous ones to be true.
Good. It may be the case that RSA is totally screwed. That tomorrow Dan Bonnet writes a new attack that kills RSA dead, but some other function turns out to be a trapdoor one-way permutation, and we're fine-ish. We're fine-ish. We actually are not fine. We'd be in bad shape, but at least this is possible. So these are different levels of assumption. Okay, so I'm going to skip over this because I think I just kind of covered it. Skip that stuff. All right, good. So we're running out of time, so I just want to set up what we're going to talk about next class. All right, so all of this brings us to the problem of writing actual security proofs for real schemes. And for the most part, this did not happen in the public world until the late 1970s and really got started in the early 1980s. Before you can write an actual formal security proof for a scheme, you first of all need to figure out what you're proving. So a big part of this work is what is a formal definition of security for a different kind of scheme. So first of all, we have to invent these formal definitions. What does it mean for encryption to be secure? We have to develop them, come up with stronger ones, and so on. And then we have to start actually building schemes that are secure under these crazy mathematical assumptions that we come up with. We start with proofs of concept, and most of them are really inefficient. And unfortunately, many of them are not efficient enough, so we have to go on using things like DES. You know, maybe we get provably secure public key encryption at first, but lots of stuff we can't prove anything about, so we just have to go on and keep using it, hash functions and so on. Things keep going. In the late 70s, early 80s, and the 90s, we start to get to, we're still in a zone where nobody's really paying attention to this provable security stuff, and everyone's just kind of guessing at how to build secure schemes. And provable schemes are still considered too expensive. Nobody's doing anything with this stuff. The question is why? Why is it that as late as the 90s, we have now provable schemes that nobody's using? And the reason is partly because some of these schemes were considered to be too expensive, but also partly because it took a while for the knowledge that we could build provably secure schemes to kind of percolate from people, from academics, out to the industry. And as a result of that, we saw a lot of really insecure crypto that unfortunately still dogs us today. And I'm running out of time, but I'll give you two examples. Okay, so RSA, we've talked about PKCS number 1 padding. PKCS number 1 padding. What did I tell you it was vulnerable to? Good. There's a padding oracle attack called the Bleikenbacher attack on PKCS number 1 padding in RSA. It's a big deal. It's an actual practical attack that breaks stuff. There is another scheme that's called optimal asymmetric encryption padding. It requires 2 invocations of a hash function and a little bit of formatting. OAP has a provable reduction to the RSA problem. And what that means is that if RSA is secure, that these attacks should not exist on encryption done using OAP. And as far as we know, that's actually held up. If you implement RSA OAP padding correctly, then you will not be vulnerable to these Bleikenbacher attacks. So what's really interesting is we actually, starting in the 90s, developed provably secure schemes that were actually resistant to real attacks. And yet PKCS number 1 is still the main padding scheme used in the TLS protocol and pretty much everywhere else. So this gives you an idea of these developments don't necessarily mean that real crypto we use gets them. And unfortunately, I have to leave you here on this kind of exciting halfway to get into what I was talking about. We'll start talking about some actual provably secure schemes next time. Wednesday, project descriptions. Doesn't mean you should start, not start thinking very hard about them until Wednesday. Like, start working on stuff, but get me something in by Wednesday. 1 per team.